Santiago Núñez-Corrales, and along with Professor Eric Jacobson at the University of Illinois, we've been developing a generalized theory of interactions for complex multiscale stochastic systems that exhibit thermodynamic irreversibility. As the motivation, we noticed that all across physics, field-based descriptions spans the way we understand these physical systems and phenomena. And conventional molecular dynamics is a particular example where this has gone to a sophistication that allows complex computations. From these examples, however, we see that the richer the behavior or the richer the structure, the more intractable field descriptions become and the more difficult it becomes to compute something from them. When we add far from equilibrium concerns, for example, when we add the inability to have continuity in some cases, this becomes a very strong challenge. However, despite the model, the interaction instants seem to remain opaque in the sense that we don't have a clear picture of what the exact objects under action are at that instant. Our contribution is to try to make those instants explicit in a way that allows to overcome several difficulties, such as the combinatorial complexity when tracing multiple hierarchies of entities. We also want to capture correctly systems for which solutions are well known, and also for those that are complex, increase the analytical feasibility. We also would like to provide a new computational path towards interaction-based modeling and simulation. We define a complex multiscale stochastic system as one in which there's microstate variety to start with, but also repertoire variety, referring to the number of interactions that are different between any two given entities in the system. We also characterize any system with varying degrees of rigidity. So we would like our theory to cover from point-like to nearly decomposable systems and fully interconnected ones. In particular, we are interested in systems for which timescale separation is not clear. A multiscale in this case, corresponds to a system with aggregation and composition of structures and functions where noise percolates from the lower scales to the upper scales, and there's cross-scale excitability. One can think of this, for example, as the role of secondary metabolites in protein networks, in which protein networks have hubs of interaction, but metabolites can cross these hubs and provide and behave in an excitable manner. We also want to have single scale, then microscale, macroscaling systems. We would like to also even move up towards scale for systems. Stochastic means, in our context, an intrinsic and combinatorial noise, dissipation, and irreversibility. In this case, we would like to capture, ideally, we would like to provide the hooks to capture reversible, locally reversible, up to closed and open systems in general. So what is the view that we have now? Suppose we have on the left side systems A and B. At present, we assume that there's an environment omega and there's a transformation that takes place simultaneously to A and B and yields A prime and B prime. That transformation usually is stated in terms of fields. However, we lack transparency of what happens at that time. And often the result of applying the transformation when translated into observables is nonlinear behavior, such as products or powers of any given quantity that is relevant. In the case of B, the model that we have proposed is the following. The environment omega sub t at any given point is a stochastic environment. This is represented by some stochastic differential equation, for example. One fluctuation. So A, in this case, can be susceptible to fluctuations. And the second part indicates that A has been susceptible to a fluctuation that has reached a sufficient threshold such that some form of messenger, it could be, for example, a particle, a force carrier, or it could be a vibration state, goes from A towards B. A relaxes, and in the process of relaxing, there's entropy that's being externalized to the system. Once the message or the messenger reaches B prime, B relaxes into B prime, there's an increase in entropy, and also at the end, two states have relaxed. In this case, the sequence that we have found here does not have any implication for simultaneity. It is, for the purpose of illustration, an indication of one of the possible sequences or one of the possible ways in which this process can occur. So more formally, we have translated that into a physical setup in which we have alpha and beta, two entities. There's an exchange of degrees of freedom between alpha and beta. That exchange between degrees of freedom is not necessarily symmetric. For example, measurement is a process where we have asymmetric exchange of degrees of freedom. Phi capital sub I represents the environment, which in this case can be granular, fluctuation based, and it is a trigger and can trigger any of these exchanges of degrees of freedom. Also, for alpha and beta, we can find a future number of possible states that we can quantify with a metric mu, in the same sense that we quantify states in statistical mechanics. And also we can find an HFRAC, which corresponds here to an observational uncertainty. Finally, we expect the frequency of the interactions to be defined in terms of the relaxation frequencies as a function of the relaxation frequencies of both of the elements present in the system. To that state, or to that effect, the general theory of interactions model poses a manifold where its quantities depart from spaces of possible configurations. Phi capital is the pseudo-extensive local context that can be field-like. It can output a quantity that can be measured, or it could be a network of other interactions when we postulate multiscale systems. We have a measurement uncertainty that depends on the extensive local context, and our dimensions of the system will be defined as random variables whose probability density function is given by a suitable distribution. For example, in the cases that we have studied so far, we are working with Ernst-Uhlenbeck processes. Now, the variables for degrees of freedom also need to reflect the fact that we have two interacting entities. Therefore, they are defined in complex space. So for the degrees of freedom, we have the degrees of freedom for alpha and beta, and correspondingly for the frequency and the generalized uncertainty, which is a measure of how the measurement uncertainty plays out with all the possible future states. We have assumed here that the measure is a logarithm to be consistent with statistical mechanics, but as we know, other choices exist. So an interaction formally is a triplet that contains the degrees of freedom, the frequency, and the generalized uncertainty. This is in complex space, but if we take the moduli of each of these quantities, we get a reduced interaction space. In the case of trying to approximate mean field theories, this pseudo-extensive context, we can suppose that the context where every interaction is the same. This doesn't have to be the case. And therefore, we define different interaction spaces, and when we add the variable time, the instantaneous view at any given point is the instantaneous interaction space. What does it mean to move across an interaction space? What it means is we're going from one particular type of interaction into another one. And therefore, there are energy and entropy considerations along the way. So moving along an interaction from a space of configurations of context configurations I to j is equivalent to performing a transformation between one interaction to the next. For a small perturbation in the context that is at least measurable, and where we can have a small subset of all the interactions in the system that may have an effect. So in essence, what we are saying through the following equation is that there's a dependence on memory effects during the interaction instant. So any interaction depends on the context, which is the f context memory function. Also, there's dependency on g, which is the internal memory function, the internal state or pseudo state that the interactions represent themselves. And also there's a compositional memory function on the interactions present at any given point in the representation of this space. So this is a very general framework, and when we attach particular functions and particular values, we make it a concrete theory of interactions. So what is the big picture? Often we have a description of systems in terms of Hamiltonians and therefore forces. And we also have extensive quantities that vary for small time frames. So what we want to do often is to compute, as in molecular dynamics, the change from one to the other by applying the forces and moving the particles or the systems where we need to. What we're doing with the theory of interactions rather is classifying these interactions. So for example, in this case, A is defined between this purple and green, and then we obtain through the appropriate definition of these degrees of freedom what is their position in the diagram of generalized uncertainty, degrees of freedom, and frequency. Then we apply transformations that are not time-based transformations, but transformations on the context that for the purpose of this example, we can consider to be equivalent to the extensive quantities. And then we can obtain, for example, aggregation properties, or we can obtain that some of these interactions disappear in favor of others appearing, and so on. So we wanted to apply this in the simplest possible model where interactions are meaningful. In this case, we wanted to do this in the hard ball or hard sphere model for hydrogen gas. We are aware that this is not a dissipative model, but we wanted to test whether this would capture correctly the behavior. And in this case, we depart from an observable, the frequency of collisions, that is well defined in this context, and we took data for the hydrogen gas. So after doing the necessary manipulations, we arrive at the defining equations of the system for degrees of freedom. In this case, we only have three positional degrees of freedom and 3 degrees of freedom from change of momentum. We can consider them those to be internal for the sake of this exercise. Also, the frequency corresponds roughly to the frequency that can be computed for collisions, and the uncertainty roughly should grow inversely proportional to the density of the system and proportional to the temperature. And our theory of interactions is one of the simplest ones. It's just one interaction between hydrogen and hydrogen with index 1. Again, this interaction is not localized. We have not assigned coordinates, but one can imagine that this is a vibration into multiple places of a system at the same time. We have the same interaction roughly, since they are distributions. So can we also specify the transformations? And we can. Because the system is not altering its constitution, it's not aggregating or disaggregating, the degrees of freedom are conserved. We always exchange 6 degrees of freedom one way or another, regardless of their magnitude. And we can provide the equations for moving across any of these dimensions. After doing so, we decided to do a Monte Carlo sampling experiment with 10,000 runs to try to map what is the space of equations defined by, or what is the space of configurations in interaction space. Each one of these points represents an interaction. And what can be observed here is that there is a very particular space of interaction space, which is occupied by all possible interactions defined by a hardball collision model. It is important to take into account, for example, that density, a quantity related to pressure regarding to general or in comparison with generalized uncertainty generates a very narrow peak, which means that at any given point, when we increase pressure, there should be a monodisperse distribution. Also, when we look at frequency against generalized uncertainty, we see a particular accumulation and a dispersion between low frequency values. But there's a general convergence. And these 2 points here correlate very strongly with what is expected by a Maxwell-Boltzmann distribution. And the same happens also for the quantity related to pressure and the frequency of the system. So the ongoing work or our work so far, well, it is not really impressive for what can be said about the theory of gases itself, really allows us to map what the ideal gas law looks like under hardball collisions. And this is a way of saying that this is what it means to be a hardball collision model. Our expectation is that with more difficult systems or systems with higher complexity and more scales of action, using the field description might imply and it might be harder to obtain some interesting answers about how to map the space of what it means to be or what a physical law implies for that system. In our case, we expect that to be easier by using our theory of interactions. So theoretically, we are working towards applying this to more particle-based systems, phase transition theory, and especially systems with no clear timescale separation. We're also working on the interaction space invariance with respect to the context memory, the interaction memory, and the system memory. Also, we would like to work, instead of using the pseudo field-like quantity, we are going to move towards interaction-based networks. In this case, the context itself would lend itself for a background-independent theory. Finally, part of the work has been moving to topos theory to try to characterize better the relationship between the interaction spaces and the dynamical spaces where quantities can be computed. At the same time, we're working on cyber infrastructure development that allows either to take a generalized or a concrete theory of interactions and produce stochastic differential equation models that are nested and coupled, or also use an agent-based simulation model that takes a concrete theory of interactions, provides the localized theory in terms of particle positions or entity positions, and then simulates forward in time. In conclusion, from these preliminary exercises, we have described the generalized theory of interactions that tries to model complex systems, focusing on explicit interaction instants. There's ongoing work towards reproducing known results across theory of gases. And what this seems to indicate is that our approach can provide a rapid calculation of steady state properties. And more than that, it can also provide a visualization of the large limit or at a large limit or the large thermodynamic limit. It can also be a potential shortcut for fields that are hard to define across what we call superphysical systems, including economics and social systems inclusive. There are two questions that are open at this point. The first one is, are interaction exclusion spaces where we don't find interactions as defined by the phenomena we're describing, and their conservation laws related? And if so, how are they related? Can we predict them by having the interaction space at the beginning? And the second open question is, how large an interaction diverse a system must be to be a representative of a thermodynamic limit? There are plenty of instances where we can identify that the number of constituent entities in a system, if these entities are simple, you need many more of them. But if they have a complex repertoire of interactions, you may need less of them to obtain the characteristic emergence of macro-scale observables that wouldn't be otherwise appearing in general. So we want to acknowledge the Illinois Informatics Program, the ACM Computational Data Science Fellowship, and the Sears in the School of Information Science at the University of Illinois. Thank you very much.